Hello, in this particular module, and it actually is a set of modules for this particular lecture, we will see how we can design oscillators. So, until now what we have seen amplifiers, we have seen the filters, and then we have to see how we can design oscillator. So, we have seen several type of filters, right, in the last lecture, right, from it was low pass, high pass, band reject, amplifiers, inverting, non-inverting, summing amplifier, comparator, right, differential amplifier. So, we see this is how we are learning about how we can use op amp for several applications. So, when you talk about oscillations, what oscillations means, right? Oscillations is something vibrating, right, that also causes the oscillation. So, how we can generate this vibrating motion, or how we can generate, if you talk about electronics, how we can generate this vibrating signal, right, which is constant, right. So, if something is oscillating at a constant frequency, we can generate oscillator. How we can arrive to this particular constant frequency, how we can design a circuit that will generate this constant frequency, right, and how the op amp will play a role in designing the oscillators. So, that we will see in this particular module. Let us see what exactly oscillators are. So, this class is about oscillators, and second part would be about noise, alright. So, right now the modules we will see what are the oscillators. This is class number 12. So, when you talk about oscillators, have you ever thought about our body, right? So, we have a brain, right, all of us have a brain, I hope and we use it. So, this is nothing but a master clock, it is our master clock, right. It tells us when to sleep, when to be awake, when we are hungry, this and that, everything is controlled by this brain, right, it is a master clock. And then we have several parts in our body which forms a signal which looks like a oscillation signal. For example, if you take a thyroid gland, or you take a skeletal muscles, myotubes, or you can take endocrine pancreas, or you can take skin fibroblast, everything you will see a certain patterns, right, you see. So, there are the oscillations are everywhere, alright, the oscillations are everywhere. If you say about energy, energy is a positive energy, negative energy, it is nothing but the oscillations around us, So, let us see kinds of oscillator and how we can design this oscillator. So, first, before we understand how we can design the oscillator, the most important point is that when we have to design an oscillator, we have to use positive feedback. In case of amplifiers, we were using negative feedback. So, oscillator is a circuit that works on the principle of positive feedback. The circuit works as a generator, generating the output signal which oscillates and generates an output which oscillates with a fixed amplitude and frequency. It does not require an input signal. That means what it says, that we can generate an output with a particular amplitude, peak to peak voltage, and a frequency, right, that is a fixed amplitude and fixed frequency, right, with the help of an oscillator, alright. So, that is a circuit that can generate output signal with fixed amplitude and fixed frequency. Second point, it will not require, or it does not require, any input signal. We will see why, okay. So, two things you have to understand about the oscillator. In short, an oscillator is an amplifier which uses a positive feedback and without an external input signal generates an output of waveform at a desired frequency. So, if I consider a non-inverting amplifier with voltage gain A, if I consider this amplifier voltage gain A. What we can see? There is a feedback network with feedback factor beta, right. There is a amplifier here with voltage gain A. There is a feedback network here which we call beta, right. The feedback is said to be positive whenever the part of output that is fed into the input is in phase with the original input signal applied to the amplifier. What does it mean? Alright. See the sentence. What it says? That the feedback is said to be positive, when the part of the output, this is output, right, when the part of the output is fed back to the input, this is the input, right, in phase means your input is this, right, your output can be in phase, your output can be out of phase, and this part is fed back to the input, that should be in phase with the input. It should be in phase. The output, the part of the output that we are feeding back to the oscillator should be in phase. So, you see here the signal, you see this schematic, the schematic is, this is your input signal, right, and this is your feedback signal, input voltage or input signal Vs, feedback signal Vf, correct. This Vi would depend on Vs plus Vf or Vs minus Vf, Vs plus Vf, Vs minus Vf. Then we have amplifier, we have output voltage, this output voltage is fed back to the feedback network and that goes back to the input signal, right. Easy, very easy, right, super easy. So, what we have learned? We have learned that when there is a feedback network beta and when we apply a output voltage, a part of output voltage is fed back to the input, it is in phase and that is why it is a positive feedback, it is said to be positive. Okay. Next is, assume that a sinusoidal input signal Vs is applied to the input, and since amplifier is non-inverting, the output signal is in phase with input. A part of output signal is fed back into input of the amplifier through the feedback network shown in figure. This is exactly what we are talking about. Here we have considered the amplifier is your non-inverting amplifier. Non-inverting amplifier means your output would be in phase with the input. In phase, that means if it is 0 degree, this is also 0 degree, right, and if it is an inverting amplifier, then your output would be out of phase, 180 degree out of phase. If I see this signal and if I see the input signal, my output is 180 degree out of phase. But here what we have considered? We have considered that the amplifier that we are using is a non-inverting amplifier. So, your output would be in phase to the input signal, right, this much is easy. So, let us quickly see once again what this slide shows us. This slide shows us few important points. One is that the oscillator uses positive feedback. Second is that the oscillator is a circuit that generates a fixed amplitude and frequency. It generates a signal with a fixed amplitude and frequency, right. Third thing, the feedback is said to be positive, or when we can see it is a positive, when the part of the output signal that is fed back to the input is in phase. Okay. So, these things we have learned in the introduction to the oscillators. Now, the amplifier gain, that is A, that is it amplifies the Vi by A times to give output voltage Vo, correct. You see this circuit, okay, this schematic. Here we are just talking about this part. So, what we see is the amplifier input is Vi, output is Vo. So, how we can define A? We can define A as Vi by Vo, correct, A is Vi by Vo. This is the open loop gain, because if I just consider this square, right, a rectangle in which my circuit is there, then there is no feedback, and that is why it is an open loop gain. It is an open loop gain. So, what we see is that the amplifier gain is A, right, that is amplifies the input signal Vi by A times to give the output signal Vo, or we can write A equals to Vi by Vo. This is the open loop gain of the amplifier. The overall input system is Vs and the net output is Vo. So, let us go back, and now what we are saying is that the overall input to this oscillator, right, is Vs and the output is Vo, correct. Overall is Vs, this is the input signal amplifier, but overall is Vs. So, Vs and Vo. So, in this particular case the overall system is Vs, output is Vo, the ratio of Vo to Vs is considered the effect of feedback, is called the closed loop gain of the circuit and is given by AF equals to Vo by Vs, right. So, in this particular case when we consider signal Vs and we consider the signal Vo, then we have to understand that this Vs and this Vo are dependent on the feedback, right, because depending on the Vf, your Vs that is applied to the amplifier would change, right, and now it is a closed loop amplifier, because we have closed the loop, and here we can have gain AF equals to Vs by Vo, that is what we have written, or Vo by Vs, right, Vo by Vs, correct. Okay. This is also okay. Now, we can also write gain equals to Vo by Vi here, okay, Vo by Vi. Okay. So, this one is done, this is done. Let us see another one. The feedback is positive and the feedback voltage Vt is added to the input signal Vs to get the input to the amplifier Vi, which is correct, absolutely correct. Why? Because if I say my feedback signal is Vt, okay, my input signal is Vs, then my Vi would be nothing but Vi equals to Vs plus Vt. Why plus? Because the signal is in phase, that is what we have written, Vi equals to feedback signal plus input signal. This Vi is the input to the amplifier. But Vt, that is feedback signal, depends on the feedback factor beta, right, because you see again this signal depends on the feedback factor beta, right. That is why what we have to write, Vt equals to beta times Vo, right, Vo is applied, part of Vo is applied to the beta, and that is why your feedback signal Vt would be beta times Vo, easy, very easy, right. So, that is why we can write Vt equals to, or feedback signal voltage, Vt equals to beta times Vo. So, what we will have, this is, if I say this is equation 1, this is equation 2, substituting equation 2 in equation 1, right, what I have? I have Vi equals to beta times Vo, or Vs equals to, so Vi equals to Vs plus beta times Vo, or Vs equals to Vi minus beta times Vo, correct, this is easy. So, substituting in the expression of AF. Now, what is AF? AF is Vo by Vs. We know what is Vs, right, we know what is Vs. So, if I substitute value of Vs in AF, what will I have? VAF equals to Vo upon Vi minus beta Vo, this is very easy, right. Now, if I divide both the numerator and denominator by Vi, what will I have? AF equals to Vo by Vi 1 minus beta into Vo by Vi, right, or AF equals to A divided by 1 minus A beta dash, because A is nothing but Vo by Vi, right, we have seen A is Vo by Vi. So, what we are writing? AF equals to A divided by 1 minus A beta dash. Now, consider value. So, here we have found out the feedback gain, the gain with feedback is dependent on gain VO by Vi divided by 1 minus A into feedback into VO by Vi, which is gain, correct. Now, consider various values of beta and the corresponding values of AF for constant amplifier gain of 20. So, if I say that A is constant 20, if I change the value of AF and change the value of beta, what I see, right, let us see. So, A is 20, if I change beta equals to 0.05, I will get AF equals to 22.22. Okay. This is constant, you see A is constant, I am only changing value of beta, I am only changing value of beta. Now, increasing the value of beta increases my gain AF, increasing further increases my gain AF, increasing little bit further makes my AF infinite, That means only a part of output signal should be feedback to the input. You see, very small part will cause very large gain, So, what does that mean? The above table shows that the gain with feedback increases as the amount of positive feedback increases. In the limiting case, the gain becomes infinite. This indicates that circuit can produce output without external input Vs equals to 0, just by feeding the part of the output as its own input. Similarly, output cannot be infinite, but gets driven into oscillations, right. Output cannot be infinite, but what will happen? It will be driven into oscillation. Other words, the circuit stops amplifying and starts oscillating. You got it? Very easy, right. See, again if we closely see what we have done, we have derived the equation of AF, right. Now, here we have kept A constant of 20 and we are increasing the beta, like you see here, this is 0.05 is less than 0.04, 0.04 is less than 0.045 is less than 0.5, that means we are increasing beta, correct. On increasing beta, we see increase in AF to the point that it reaches to infinite. Now, actually it cannot be infinite, that means it will start oscillating. So, in other words, the circuit will stop amplifying and start oscillating, right. It will stop amplifying and start oscillating. What important things that we have to learn from this slide? That only a part of output signal is fed feedback to the input, or beta is extremely small. So, to understand the oscillator, we have to understand a very important criteria called Bar-Hussein criteria. So, what is that Bar-Hussein criteria and why we have to learn to understand the oscillator, alright. So, we will see today what exactly is the Bar-Hussein criteria and why it is important to understand, so to get the idea how the oscillations would work, alright. So, if you see the screen, what we find is that considering a basic inverting amplifier with an open loop gain A, the feedback network attenuation beta is less than a unity. As a basic amplifier is inverting, it produces a phase shift of 180 degree between input and output as shown in figure, right. One thing we have seen, what? That if I apply input signal and if I consider my amplifier to be inverting, then my output signal would be 180 degree out of phase with respect to input, right. This is what is written, first sentence. Okay. This is easy to understand. Now, let us see. Now, the input Vi is applied to the amplifier, right. Vi is applied to this amplifier is to be derived from its output voltage using feedback network. So, this feedback network should be there, some feedback network should be there, right, to which this VO should be fed, and this would be fed to your VI, so that your Vs can be determined, correct, that is what we have seen. So, but the feedback must be positive, right, that means that if I feed part of this voltage, if I feed back to the input of the oscillator, this the phase here is 180 degree out of phase, but here I want same phase, here I want same phase, because this is a positive feedback, right, we have just seen. Here it is 180 degree out of phase, here I want same phase. So, what is the written here, that but the feedback must be positive, that is voltage derived from the output using the feedback network must be in phase with input Vi, correct, that we have seen. Thus, the feedback network must introduce a phase shift of 180 degree, is it correct. So, you see very easy to understand, okay, very easy to understand, do not get confused, it is very easy to understand. What is saying is that if I apply input signal which is like this, if I see output signal which is 180 degree out of phase, I have to provide a part of the output signal back to the input through my feedback network beta, right, this I know, this we have seen, right, part of the output is fed back to the input through feedback network beta. So, part of the output how it looks like this. Now, this is 180 degree out of phase, right, compared to the input, but we know that the input should be in phase, the part of the signal that is provided back to the input should be in phase, that means my feedback that is provided back to the input should be 0 degree, but here it is 180 degree. How can I make it 0 degree? So, this 180 degree, if I introduce a phase shift of 180 degree in my beta, if I introduce a phase shift of 180 degree in my feedback network, then 180 degree plus 180 degree, that will be my 360 degree. 360 degree is equal to 0 degree, correct, 0 and 360 degree are same. That means that my beta, that is feedback network, should introduce a phase shift of 180 degree if my amplifier is an inverting amplifier, which is causing my output to be out of phase with respect to input. That is why my output is 180 degree out of phase, and then this output, part of this output is fed back to the input through beta, which is feedback network. It has to again have 180 degree phase shift, which is provided by my feedback network beta. This is what is written. Thus, the feedback network must introduce a phase shift of 180 degree while feeding back the voltage from output to the input. This ensures the positive feedback. And this arrangement, whatever we are drawing here, is already shown in the figure here, correct. So, if we see input signal 0 degree, 180 degree phase shift because inverting amplifier, so 180 degree, part of output is feedback to the input, this is 180 degree phase because it is same voltage which is VO, right, a part of the voltage. Here you see this is similar to 0 degree, right. So, this phase shift is introduced by feedback network beta, correct. This is what is shown here, and this is how the things work. So, first thing we understood that inverting amplifier, then we have to use a feedback network which can introduce 180 degree phase shift. Now, considering a fixed voltage Vi applied to applied at the input of the amplifier, what we get is Vo equals to A times Vi. The feedback network beta decides the feedback to the given to the input. So, Bf is nothing but beta times Vo. On substituting the value, what we get? So, we know this Vo equals to AVi, we have Vf equals to beta Vo. So, if I substitute the value, we have Vf equals to beta times AVi. Right. for the oscillator we want that the feedback should drive the amplifier, hence Vf must act as Vi, correct. This is also easy. For the oscillator what we want, the feedback should drive the amplifier and hence Vf, that is feedback voltage, must act as a input voltage. Therefore, we can write Vf is sufficient to act as Vi when we have A beta equals to 1, right. You see, this is feedback network, right, feedback voltage. Feedback voltage is gain into beta into Vi. So, but in reality what we want, Vf should be equal to Vi, right, feedback voltage should drive the amplifier. So, to do that, what is the thing that we require, that this A and beta, the mode of A beta should be 1. Second thing, the phase of Vf is same as Vi, right. This is first thing, alright. Let us say A. Second is phase of feedback, so we say B, alright. That is feedback network should introduce 180 degree phase shift in addition to 180 degree phase shift introduced by inverting amplifier. If we are using inverting amplifier, this ensures positive feedback. So, the total phase shift is 360 degree or 0 degree. That means my Vf and Vi are in phase, correct. You got it. First thing is that my Vf should be equal to Vi, and to get that my A beta should be equal to 1. So, that is my first condition. My second condition is the Vf and Vi should have same phase, right. So, in this condition Vf drives the circuit and without external input circuit works as an oscillator. The above two conditions, which are conditions? Condition 1. So, let me remove this, so it is not confusing anymore. Let us say this is condition 1, this is condition 2, right. The above conditions required to work the circuit as an oscillator are called the Bar-Coussin criteria for oscillation. Okay. So, whenever somebody asks what are the Bar-Coussin criteria for oscillations, we can say that there are two criteria. First is that A into beta, mode of A into beta should be 1. Second condition is that Vf should be in phase with Vi, or the feedback signal should be in phase with the input signal, right. So, if we are using an inverting amplifier, feedback should introduce 180 degree phase shift. If we are using a non inverting amplifier, feedback should not introduce any phase shift, right. So, the Bar-Coussin criteria states that 1. The total phase shift around a loop as the signal proceeds from input through the amplifier feedback network back to the input again, completing a loop should be 0 degree or 360 degree, right. Total phase shift should be 0 degree or 360 degree, that is the first criteria. That means, if I apply an input signal, my output signal is feedback through the feedback network to the input of the oscillator, then my output which is feedback through the feedback network should be in phase with the input signal, that is my first condition, right. So, if it is my output voltage is out of phase, then my feedback network should provide a 180 degree phase shift. If my output is in phase with the input, my feedback network does not require to provide any phase shift. So, two things you have to remember, right. Second thing is, first thing is this, second thing is the magnitude of the product of open loop gain of the amplifier and feedback network. What is the open loop gain of the amplifier? A, and what is feedback network? Beta, right. So, magnitude of the product of open loop gain of the amplifier and the feedback network should always be equal to 1. Why? Because we have seen that Vf, that is the feedback voltage, is equal to A into beta into Vi, and Vf should be enough to drive the input signal. To meet this condition, Vf should be equal to Vi. To meet that condition, A into beta equals to 1. So, two conditions when you remember, then you understand what exactly is a, or what exactly is a Bar-Coussin criteria and what does it states. Okay. So, if you come back on the screen, what you see is that if you satisfy this both the conditions, if you satisfy first two condition, then the circuit works as an oscillator producing a sustained oscillations of constant frequency and amplitude. If you satisfy these conditions, the circuit works as an oscillator producing sustained oscillation of constant frequency and amplitude. In reality, no input signal is needed to start the oscillation. In practice, A beta is made slightly greater than 1 to start the oscillation, and then it adjusted itself to equal to 1, finally resulting in a sustained oscillation or self sustained oscillation, right. So, ideally there is no input required, but practically or in practice what we will do, we will have A into beta should be slightly greater than 1, and then it comes back to A into beta becomes equal to 1. Once the oscillation start, the A into beta becomes gets equal to 1. Okay. Now, we will see the effect of A beta on the nature of oscillations. So, now once you know, right, how the things works, let us see how what is the effect of product of A into beta on the oscillations. Okay. So, let us see that if I have A into beta product of my gain into feedback greater than 1, what will happen? I will see when my A beta equal to 1, what will happen? I will see when A beta is less than 1, what will happen, right. So, if you see the screen, what we see is when I have a mode of A into beta greater than 1, then when the total phase shift around the loop is 0 degree and A beta phase shift is 0 degree and A beta is greater than 1, then the output oscillates, but the oscillations are growing type. The amplitude of oscillation goes on increasing as shown in figure, right. That means, if I keep A beta is greater than 1, my output oscillations will start growing, it is growing, it keeps on growing, okay. It keeps on growing, all right. Let us see, if I have A mode of A into beta equal to 1, in this state what will happen? When total phase shift around the loop is 0 degree or 360 degree, ensuring a positive feedback, and A into beta equals to 1, then the oscillations are with constant frequency and amplitude and are called sustained oscillations. What are they called? Sustained oscillations. When you have A into beta mode of A into beta equal to 1, and you can see here the sustained oscillations. Oscillations are constant, frequency constant, voltage peak to peak voltage constant, and that is why they are sustained oscillations. Okay. Now, if I have A into beta mode of A into beta less than 1, what will happen? When the total phase shift is 0 degree or 360 degree, but A beta is less than 1, then the oscillations are of decaying type. Such oscillation amplitude decreases exponentially and the oscillation finally ceases down. You see, the oscillations are decreasing and it looks like they are decaying, and finally they will cease down, they will die, right. So, the circuit works as an amplifier without oscillations, and decaying oscillations are shown here in the figure. So, the start the oscillation without input, A beta is kept little bit higher than unity, and then the circuit adjusts equal to 1 to result in the sustained oscillation. Alright guys, you now know why we require A beta equals to 1. The obvious question here is that if no input is required, how will oscillation start? How we can have oscillations? Alright. And from where does the starting voltage come from? There are two questions, right. How, if we are not applying any input, how oscillations can start, and if there is a starting voltage, from where it is coming, from where the starting voltage is coming. So, these two signals we have to understand how the oscillation starts and from where the signal is, where the voltage is coming. So, the starting voltage. the starting voltage of the oscillator. So, every resistance, you see the resistance in the oscillator circuit, every resistance has some free electrons. Under the influence of normal room temperature, these free electrons moves randomly in a various direction, right. Such a movement of free electrons generates a voltage called noise voltage. All right. What is said? That every resistance has some free electrons. Now, in room temperature, so now we have to understand the semiconductor devices and physics of semiconductor devices to understand that how the free electrons are there, how the free holes are there in the room temperature, how the movement occurs. But let us assume that we know how does these things happen, and thus we are assuming that there are free electrons and these free electrons will start moving randomly, all right. That how they will move randomly in the because of the effect of room temperature. There are few electrons that will start moving randomly. This free movement of this electron will cause a noise. This will cause a noise across the resistance. Such noise voltage present across the resistance are amplified, right. Resistance has free electrons move at the room temperature, that causes a noise voltage. This noise voltage presence across the resistance are amplified because we have an oscillator circuit. If you come back to the screen, what we see is that when this voltage is present across the resistance are amplified, hence to amplify such small noise voltages we have to keep A beta greater than 1, slightly greater than 1, right, to start what? To start the amplification. Amplification of what? Amplification of small noise voltage. Small noise voltage generates from where? Some small noise voltage generates from the free electrons, right, that are present in the resistance and that are moving randomly in various direction in normal room temperature. Easy. Now, once we start the amplification, such amplifier voltage appears at the output terminals. The part of output is sufficient to drive the input of the amplifier circuit, then the circuit adjusts itself to equal to 1 and phase shift is 360 degree or 0 degree. So, we can get a sustained oscillations, all right. So, this is how the starting voltage is there in the starting voltage is there when we have to use an oscillator circuit, So, let us see example, okay, interesting. So, the problem is let us read the statement. In a certain oscillator circuit, the gain is given and the feedback is given. Verify Bar-Coushain criteria for sustained oscillation. Also find the frequency at which the circuit will oscillate. So, what is our criteria? A into beta should be equal to 1. Second is phase shift, phase should be 0 degree, phase of the input provided through the feedback, right. Third would be we require to find frequency at which the oscillations will start. This we are asked. What we are given? We are given gain is given and then beta is given, correct. So, A is given, beta is given. To verify Bar-Coushain criteria, which means we have to verify A beta equal to 1 at a frequency for which phase shift 0 degree. So, let us express A beta in a rectangular form. When we have to express it in rectangular form, how will write? A into beta is this value. So, if I further work on this equation, what will I get? I will get this value. Now, if I rationalize the denominator, so again guys, you see you have to understand mathematics, okay. This is very basic mathematics, So, I am presuming that it is presumed that you know these things, all right. So, A into beta is this, we have this equation, I have to rationalize the denominator and so we have this particular equation, is it. On solving this equation, what will I have? A beta equals to this particular equation, right. Now, A beta equals to 0 degree, right, that is a criteria. So, imaginary part of A beta must be 0. So, which is the imaginary part? In this particular equation? We have to see and make it 0. This is possible when we have omega into this value equals to 0. You see here, where is the imaginary part? Imaginary part is here, right, this part, right, this part, you see imaginary part. So, we have written the imaginary part equals to 0, omega equals to 0, or 4 into 106 for 10 to the power 6, this is power 6, minus omega square equals to 0, or omega square equals to 4 into 10 to the power 6, or omega equals to 2 into 10 to the power 3 radian per second, right. At this frequency A beta can be obtained as A into beta, we will multiply at this value which is 10 to the power 3, 10 to the power 3, right. Then we will have A beta equal to 1. When we solve this equation, what we will find? A beta equals to 1, right. That is what we want, that is what we want. At omega equal to 2 into power 10 to the power 3, we have A beta equals to 0 degree, as imaginary part is 0, while A beta equals to 1. Thus, the Bar-Crutzen criteria is satisfied, correct, because A beta is 0 degree and the A into beta is 1. So, phase is 0 and the mode of A into beta is 1, that is how we have solved the problem. So, now we know that yes, this satisfies the Bar-Crutzen criteria, but we are asked to also find the frequency at which the oscillations will start, is not it. So, let us find the frequency, alright. So, if you see the screen, what we see that the frequency at which the circuit will oscillate is a value of omega for which A beta equals to 1 and phase shift is 0 at the same time. Since omega equals to 2 pi f or f equals to omega by 2 pi, we know the value of omega, omega is 10 to the power 3 by 2 pi or 318.309 hertz, 318.309 hertz, right. This is my mistake. So, just consider this 10 to the power 3, okay, 10 to the power 3. So, it is very easy, right. Omega we already know, omega is 2 pi f or f equals to omega by 2 pi. We already know what is omega, omega is 2 to the power 10 raised to 3, 2 into 10 raised to power 3 into 10 radian per second. So, we substitute the value and we get value of f equals to 318.309 hertz, which is the starting frequency for the oscillators. So, we have found out that this satisfies Bar-Crutzen criteria and we have found out the value of frequency. Two things we have found out, right. So, what we have seen, guys, in this particular module, we have seen how the oscillator works, right. What exactly is an oscillator, what are the minimum requirements for a circuit to become an oscillator, that is our Bar-Crutzen criteria, and then we have seen that if we have A into beta greater than 1, what will happen, right. If it is equal to 1, what will happen, if it is less than 1, what will happen, and we have also solved a problem to understand or verify whether the given set of values in the problem satisfies the Bar-Crutzen criteria or not, right. Now, what we will see in the next module, we will see that how we can classify the oscillators, right, classify the oscillators. Until now what we have seen is what are the oscillators and what are the criteria for the oscillator. Next module we will see the classifications of the oscillator and we will go on from that particular point. Till then you again see whatever is taught in this particular module, right, and I will catch you in the next module. Till then you take care.